At Neptune, the sun no longer looks like the sun. It is still the same star. It is still the engine that holds Earth, Mars, Jupiter, Saturn, and every remembered sunrise in its gravity. But from 30 astronomical units away, it has shrunk into a hard white point, brilliant enough to cast a faint noon, too small to feel like a day. Earth is worse. Earth is not a blue marble from there. It is not the Apollo photograph turned inside out. To human eyes, without optics, Earth is gone. That is the first uncomfortable truth about the last major planet. The first humans to reach Neptune would not merely be far from home. They would live in a place where home has fallen below the threshold of direct experience. They could calculate Earth's position. They could point a telescope at it. They could receive recorded voices from it, delayed by hours. But they could not look out a window and see the world that made them. They could not call mission control and hear an answer while the problem was still unfolding. They could not count on rescue because rescue would not be late. It would be physically meaningless. The familiar story says Neptune is another destination. Harder than Mars, colder than Jupiter, more distant than Saturn, but still part of the same map. The sharper argument is stranger. Neptune may be inside the solar system, but for human beings it may sit beyond an exile horizon, a distance where exploration stops being an extension of home and becomes a form of permanent separation. The strongest objection is real. A sufficiently advanced civilization might send humans there. Nuclear power, closed-loop life support, artificial gravity, autonomous medicine, robotic repair, perhaps even propulsion systems far better than anything we have flown, could make a Neptune expedition physically possible. But possible is not the same as continuous with everything we have called human spaceflight. Neptune forces a different question. Not can a spacecraft reach the 8th planet, but can human beings go that far and still remain socially, operationally, and emotionally connected to the world that sent them? That is the debate. Not whether Neptune exists within our gravitational neighborhood. It does. Not whether robots can get there. One already did. The question is whether the same solar system that feels familiar in diagrams contains, within its own borders, a distance large enough to turn explorers into exiles. The schoolroom diagram never warned us. You know the image. The sun on one side, the planets arranged in a neat row, each separated by a modest white gap. Mercury, Venus, Earth, Mars. Then the larger worlds, Jupiter and Saturn, their rings and storms making the poster beautiful. Then Uranus and Neptune at the far end, perhaps a little smaller on the page, perhaps tinted blue, but still included in the same comfortable sequence. The image is useful for naming things. It is terrible for understanding them. No honest scale model can fit on a wall. The inner solar system is cramped. The outer solar system is not merely wider. It opens into a different regime of distance. If the sun were a basketball, Earth would be a tiny bead less than 1/10 of an inch across, sitting about 86 feet away. Mars would be another tiny bead, roughly 130 feet from the ball. Jupiter would sit several hundred feet out. Saturn farther still. You could make the walk. It would be inconvenient, not unimaginable. Then the model begins to punish intuition. Uranus lies far enough away that the walk becomes a neighborhood journey. Neptune sits roughly half a mile from the basketball, a pea-sized world at the far edge of the model, separated from the rest by empty space so large that the sun itself would be lost behind buildings, trees, and ordinary human geography. In the real solar system, this is not a poetic exaggeration. Neptune is about 30 times farther from the Sun than Earth is. Sunlight there is roughly 900 times weaker than the light that falls on our planet. High noon on Neptune would resemble dim twilight on Earth, not the golden day our bodies evolved to expect. Neptune's average distance from the Sun is about 2.8 billion miles, or 4.5 billion kilometers. One astronomical unit is the distance from Earth to the Sun. Neptune sits at about 30 of them. From that distance, even light needs about 4 hours to travel from the Sun to the planet. A radio signal obeys the same speed limit. A message from a spacecraft at Neptune takes hours to arrive at Earth, and the reply takes hours to return. This is where distance becomes more than distance. It becomes latency. It becomes operational isolation. It becomes a new kind of silence. On the International Space Station, astronauts orbit a few hundred kilometers above Earth. They are in space, but Earth is not absent. It fills the windows. It fills the schedule. It fills the radio. Mission control speaks almost instantly. A medical specialist can ask a question and hear the answer while the patient's condition is still current. An engineer on the ground can study telemetry, consult a room full of experts, and talk a crew member through a repair while the tool is still in the crew member's hand. Family calls are imperfect, but recognizably human. The astronaut speaks, someone answers, and both people share a present tense. Even the moon did not break that present tense. Apollo astronauts heard Earth with only a short delay. They could look back and see the whole planet, not as an idea, but as a luminous body in the black. Apollo was dangerous, but home remained visible. Earth was a place they could point to. Mars begins to strain the bond. Depending on the planet's positions, messages can take several minutes to more than 20 minutes one way. A conversation becomes awkward. Emergency support slows. Crew autonomy becomes not a virtue, but a requirement. NASA treats this delay as one of the serious human factors in deep space missions, because even modest communication delays can disrupt teamwork, increase workload, and change how crews experience support. Mars is already a step away from the real-time human web that has supported every spaceflight so far. Neptune is not a step. It is a category change. Imagine a crew member at Neptune reporting smoke inside an electronics bay. On the station, ground controllers would join the emergency in seconds. At Neptune, the report travels outward through the vacuum for roughly 4 hours. By the time Earth hears the first words, the fire has either been extinguished, contained, spread, or ended the mission. Engineers can still respond. They can still analyze. They can still send guidance. But their guidance arrives in a world that has already changed. It is not help in the ordinary sense. It is advice sent to the aftermath. This is the first great fracture in the dream of sending people to Neptune. Human spaceflight has never been just astronauts and machines. It has been astronauts embedded in a planetary support system. Every orbital mission is the visible tip of a vast structure. Flight surgeons, trajectory analysts, communication specialists, systems engineers, psychologists, meteorologists, recovery teams, supply chains, training staff, simulation rooms, and factories. We celebrate the crew because they take the visible risk, but the crew survives because Earth surrounds them with invisible competence. At Neptune, Earth cannot surround them. It can only send delayed echoes. The planet itself is worth the journey, at least scientifically. Neptune is not a passive blue ornament at the edge of the poster. It is one of the most violent and least understood worlds in the solar system. It is an ice giant, not in the everyday sense of a ball of frozen water, but in the planetary science sense. A world whose mass includes large amounts of volatile compounds, such as water, ammonia, and methane, compressed into hot, dense, exotic states above a rocky core. Its atmosphere is mostly hydrogen and helium, with methane absorbing red light and giving the planet its blue color. Its diameter is about 4 times Earth's. Its mass is about 17 Earths. And somehow, under sunlight 900 times weaker than ours, Neptune drives the fastest winds measured on any planet in the solar system. Clouds of methane ice are carried by winds exceeding 1,200 miles per hour. Storm systems large enough to swallow Earth appear, evolve, and vanish. Voyager 2 saw the Great Dark Spot in 1989, an enormous dark vortex in Neptune's southern hemisphere. When later telescopes searched again, that particular storm had disappeared. Neptune does not keep its face still. It creates weather from an energy budget that should, at first glance, be too poor to support such violence. The reason is partly internal heat. Neptune emits significantly more energy than it receives from the Sun, roughly a few times the absorbed solar input. That heat rising from within helps drive atmospheric motion. But the details are still not fully settled, because the only spacecraft ever to visit Neptune did not orbit it. It flew past. Voyager 2 left Earth in 1977. It used a rare geometry of the giant planets to perform gravity assists at Jupiter, Saturn, Uranus, and finally Neptune. That alignment was not a small convenience. It was the reason the grand tour was possible. By falling through the gravity wells of the outer planets in sequence, the spacecraft gained speed and changed direction without carrying the impossible propellant load a direct chemical journey would have demanded. 12 years after launch, on August 25, 1989, Voyager 2 swept past Neptune and gave humanity its first close look at the 8th planet. Even that robotic success exposed the distance. At Neptune, the sunlight was so faint that Voyager's camera required longer exposures, but the spacecraft was moving so fast that long exposures would smear the images. Engineers programmed the spacecraft to rotate during imaging, panning with the target like a photographer tracking a moving car, except the photographer was a robot billions of miles away, and the command sequence had to work without human correction in real time. The radio signals were so weak that the Deep Space Network had to be upgraded and combined with additional antennas to receive data efficiently. The spacecraft used a transmitter with a power level almost absurdly small compared to the distance it crossed. The encounter was a triumph. It was also a warning. If Neptune was that hard for a small robotic probe that did not need air, water, food, medical care, privacy, sleep, or hope, then a human mission belongs to a different universe of engineering. A robot can fly past and keep going. A human crew cannot. A robot can accept a one-way trajectory because it has no body to return. It has no family waiting for a reunion. It has no bones to lose calcium, no blood volume to shift, no immune system to weaken, no psychology to fray under confinement. A robot can pass through the outer solar system as a message in metal. A human spacecraft must be a habitat, clinic, farm, workshop, power plant, and community, all wrapped inside shielding and launched across a gulf where every kilogram matters. The propulsion problem comes first because it is the one people see most easily. Neptune is not simply far. It is far enough that every feasible trajectory becomes a negotiation with time, mass, and fuel. Voyager 2 reached Neptune in 12 years because it did not stop. It could fly by at high speed, collect data, and vanish outward. A crewed mission would need to slow down, either to orbit Neptune, rendezvous with Triton, or conduct a sustained scientific campaign. Deceleration is not a detail. It is half the mission. Every meter per second of velocity you must remove at Neptune requires propellant, power, or some other mechanism carried across the whole journey. And if the crew is supposed to come home, the problem doubles and then multiplies. They must leave Earth, cross the solar system, slow at Neptune, live and work there, depart Neptune, cross back, and slow again at Earth. The rocket equation does not care that this is emotionally necessary. It only cares about mass ratio. The propellant for the return leg must be transported outward. The propellant for transporting that propellant must also be transported. The spacecraft swells. The launch architecture becomes not a large rocket, but an industrial campaign. Chemical propulsion, the tool that got humans to the moon, cannot make a practical crewed Neptune expedition. Nuclear thermal propulsion could improve performance within the solar system and may one day reshape missions to Mars and beyond. But the leap from better transit times to a sustained human expedition to Neptune remains vast. Nuclear electric propulsion could use fuel more efficiently, but generally trades thrust for endurance, producing slow spirals and long cruise phases. Fusion propulsion, if it becomes compact, reliable, and space-qualified, could change the debate, but it is not an available mission architecture. At present, Neptune remains a destination that we can imagine scientifically long before we can design human logistics around it. The strongest counterargument begins here. Human beings are not limited to today's engines. It would be foolish to declare that no future propulsion system could carry a crew to Neptune and back. History is full of technologies that appeared impossible before supporting infrastructure made them routine. A 21st century engineer should be humble about what a 23rd century civilization might build. Nuclear reactors may become safer and lighter. Closed-loop life support may become robust. Artificial gravity could reduce medical damage. Autonomous repair systems may become far more capable than anything aboard current spacecraft. If the claim is that humans can never reach Neptune under any circumstances, the claim is too strong. Even if the vehicle succeeds, Neptune crosses a distinctly human threshold. The point where travel becomes separation and return can no longer be assumed. The hard part is not only getting bodies there, it is preserving the conditions that make a mission human rather than merely biological transport. A Neptune trajectory lasting 12, 15, or 20 years one way does not resemble a Mars mission extended. It resembles a life stage. A crew that launches in their 30s arrives in middle age. If the mission returns, they may come back as elders. They would spend the most productive decades of adult life inside a sealed machine, surrounded by the same few faces, living in a schedule written by orbital mechanics rather than by seasons, cities, or families. The mission would not interrupt life. It would consume it. The body is not passive during that time. In microgravity, bone density falls. Muscles weaken. Fluids shift. The cardiovascular system adapts to the absence of weight. Exercise helps, but does not erase the problem. Space agencies have learned a great deal from long stays on stations, but those stays occur in low Earth orbit with return possible and medical support nearby. The longest continuous human spaceflight lasted a little over 14 months. A Neptune transit would be measured in decades if it included return, and even the one-way leg alone exceeds every continuous human spaceflight by an order of magnitude. Artificial gravity is the obvious answer, and it should be taken seriously. A rotating habitat could create centripetal acceleration that mimics gravity. If designed well, it could reduce bone loss, preserve muscle function, help cardiovascular health, and make ordinary life more tolerable. It might be one of the enabling technologies for any serious human journey beyond Mars. But artificial gravity brings its own engineering demands: rotating structures, bearings or non-contact rotation systems, vibration control, mass distribution, emergency docking between rotating and non-rotating sections, and long-term reliability over millions of rotations. A rotating habitat does not make the journey short. It only makes the biology less impossible. Radiation remains. Beyond Earth's magnetosphere, crews are exposed to galactic cosmic rays and solar particle events. Shielding can reduce dose, especially against lower energy particles, but high-energy cosmic rays are difficult to stop without massive shields, and heavy shielding can create secondary radiation when struck by energetic particles. A Neptune mission would spend years in deep space, and then years at a destination where solar power is weak and fast evacuation impossible. Radiation is not a cinematic threat. It is cumulative damage. DNA breaks, cancer risk, potential neurological effects, cataracts, cardiovascular concerns, and uncertainty piled over time. The counter-argument again deserves respect. Engineers can design storm shelters surrounded by water, food, fuel, or waste tanks. Mission planners can choose trajectories that avoid periods of high solar activity, or at least model them. Future materials may offer better protection. Biological countermeasures may improve. We should not pretend radiation alone makes Neptune forbidden. But radiation does not operate alone. It combines with confinement, distance, aging, maintenance, and the impossibility of rescue. Each risk may be manageable in isolation. Neptune's danger is that none of them remains isolated. Life support is the next boundary. A crew cannot carry Earth with them, but they must carry enough of Earth's functions to survive. Oxygen production, carbon dioxide removal, water recycling, temperature regulation, waste processing, food storage or food growth, microbial monitoring, medical capacity, and repairs. Current spacecraft life support is sophisticated but not fully closed. The International Space Station recycles water at impressive efficiency, and recent upgrades have demonstrated recovery near the 98% goal considered important for deep space missions. But the station still depends on Earth. It receives cargo. It receives spare parts. It receives replacement hardware. It can be evacuated. A Neptune-bound spacecraft receives none of those things. A water recovery system that works well for a year is not automatically a system that works for 15 years without resupply. A filter clogs. A pump bearing wears. A valve sticks. A sensor drifts. A membrane fouls. A catalytic reactor becomes less efficient. None of these failures is dramatic enough to dominate a movie trailer, but each can become fatal if the replacement part is not aboard or cannot be manufactured. A spacecraft to Neptune must therefore carry not only life support systems, but the ability to keep life support systems alive. That recursive burden is one of the least appreciated barriers in long-duration spaceflight. You need tools to repair the machine. Then you need tools to repair the tools. You need diagnostic devices to detect failures before they become emergencies. Then you need calibration standards to keep the diagnostic devices trustworthy. You need spare electronics. Then you need radiation-hardened storage that preserves spares for years. You need software. Then you need the ability to verify that the software has not been corrupted by radiation, aging hardware, or human error. Each layer added for safety becomes another layer that can fail. Food is even more intimate. Stored food for a small crew over 15 years is heavy and nutritionally uncertain. Vitamins degrade. Packaging ages. Texture and variety matter for mental health as well as calories. Growing food aboard offers freshness, psychological benefit, and partial closure of the life support loop. But it also introduces ecology into a machine. Plants need light, water, nutrients, temperature control, microbial balance, and human attention. A fungus in the root zone is not a gardening problem when your garden is part of the life support system. It is a mission threat. Belonging matters here, but the reasoning must become more careful and exact. Neptune does not make all these systems impossible by magic. It removes the margin that allows failure to be repaired from outside. On Earth, almost every machine is part of a planetary economy. If a pump fails, a supply chain exists. If a medicine runs out, a pharmacy exists. If a specialist is needed, a hospital network exists. In low Earth orbit, a miniature version of that planetary economy still reaches upward through cargo vehicles and real-time support. At Neptune, the economy ends at the hull. This is why rescue is the central moral and operational problem. We often describe space missions by their destinations, but human spaceflight has always been structured around return. The spacecraft is designed not merely to go, but to bring the crew back. Apollo's achievement was not reaching the moon alone. It was returning living human beings through fire and ocean to the planet that launched them. Even Apollo 13, the great survival story of spaceflight, was saved by distance as much as ingenuity. The crew was close enough for mission control to matter in real time. Close enough for the moon's gravity to help bend them home. Close enough that the emergency remained inside the reach of human response. At Neptune, the phrase, "bring them home," loses its ordinary meaning. A rescue mission launched after a failure cannot arrive in time. A resupply craft cannot be dispatched like a cargo vehicle to a station. A medical evacuation is impossible. A return vehicle, if carried, must survive the outward journey, remain operational at Neptune, and then sustain the return leg across another decade or two. The architecture becomes so large, so expensive, and so failure-prone that the most honest mission designs begin to drift toward one-way logic, even if no one wants to say so. This is the part of the debate where optimism often becomes evasive. It is possible to say that future propulsion will solve it. It is possible to say that a crew would accept the risk. It is possible to say that humanity has always sent people into danger and that every frontier looked impossible before someone crossed it. There is truth in that. But Neptune is not an ocean. It is not Antarctica. It is not even the moon. Every historical explorer remained inside a biosphere. Every ship crossed water under the same atmosphere as home. Every polar expedition existed on a planet where a rescue party could, in principle, move through the same environment. Neptune is separated by vacuum, radiation, orbital mechanics, and light speed delay. Comparison to older exploration can inspire courage, but it can also hide the newness of the problem. The first humans at Neptune would not simply be farther than anyone before. They would be beyond the real-time consequences of compassion. People on Earth could care. They could watch. They could grieve. They could work desperately. But if the crew's oxygen system failed, care could not cross the distance fast enough to become oxygen. If a surgeon on Earth knew exactly how to save a patient, that knowledge could not arrive in time to guide the hands in the moment. If a family wanted to speak one last sentence to someone dying at Neptune, the sentence would arrive after the death or be received by someone already gone. This is not melodrama, it is causality. The solar system contains many forms of danger. Mars has dust, radiation, low gravity, and distance. Jupiter has lethal radiation belts and immense gravity. Saturn has complexity and cold. Uranus and Neptune have weak sunlight and long travel times. But Neptune adds something more complete. The combination of extreme travel duration, 4-hour one-way communication, near useless solar energy, no practical rescue, and a return problem so large that the words crude expedition begin to shade into exile. Power is one reason. Solar arrays that work near Earth become ineffective far from the Sun because sunlight falls with the square of distance. At Neptune, a solar panel receives about 1/900th the sunlight it would receive near Earth. For a small robotic probe, radioisotope power can work. Voyager used radioisotope thermoelectric generators. Future robotic missions to the outer solar system often rely on radioisotope systems or nuclear power concepts. But a human spacecraft requires far more electricity, environmental control, communications, computing, lighting, thermal management, medical equipment, propulsion subsystems, scientific instruments, and possibly agriculture. Nuclear power becomes almost unavoidable. Radioisotope generators are reliable but low in power for crude needs. Fission reactors offer higher power but introduce reactor safety, heat rejection, moving parts or conversion systems, and long-term maintenance. A spacecraft far from the Sun must also manage waste heat carefully. Heat is precious for survival and a problem for machinery. The crew lives between cold emptiness outside and delicate thermal balances inside. The spacecraft is not simply traveling through darkness. It is carrying an artificial climate through a region where the Sun can no longer power civilization in miniature. The human nervous system evolved under cycles of light and darkness, changing weather, open horizons, social variety, and the living presence of a planet. A Neptune mission would ask a handful of people to live for years in an environment of planned monotony. The same walls, the same tasks, the same people, the same maintenance logs, the same delayed messages, the same narrowing margin. This is not merely boredom. It is a slow attack on time perception, identity, and meaning. Isolation studies on Earth can tell us something, but not enough. Antarctic winter-over crews experience months of darkness and confinement, yet they remain on Earth. Submarine crews experience sealed environments, yet they know the ocean above them belongs to the same world, and that port exists. Mars analog crews can simulate delay and isolation, but everyone in the habitat knows the door opens onto Earth. Neptune would remove the hidden reassurance that makes every analog psychologically tolerable. The door does not open onto Earth. It opens onto vacuum, and beyond the vacuum lies a return journey measured in decades. The strongest psychological counter-argument is that crews could be selected and trained for this. Humans adapt. They create meaning in prisons, monasteries, ships, polar stations, and long migrations. A Neptune crew would not be randomly chosen. They would be among the most psychologically prepared people ever assembled. They would have private habitats, rich digital libraries, immersive virtual environments, strong group cohesion, and years of training. They might build a culture aboard the spacecraft, one that does not depend on constant emotional reinforcement from Earth. Perhaps they would not experience exile as horror, but as purpose. That objection matters. It prevents the argument from becoming simplistic. Isolation is not automatically collapse. Some people seek distance. Some missions generate meaning precisely because they are irreversible. A crew that freely chooses Neptune might understand their journey not as loss, but as the most complete act of exploration in human history. But consent at launch is not the same as lived experience in year 12. The person who signs the document on Earth is not exactly the person who wakes up a decade later with a shrunken son outside the window, aging parents on delayed video, a failing valve in the water system, and another 8 years before any possible return burn. Human beings change. Meaning changes. Psychological resilience is not a stored consumable you can load before departure. It must be renewed, and the sources of renewal become thin at Neptune. This is why the title, if spoken honestly, is not only about whether a return trajectory can be calculated, it is about whether Earth can remain Earth across such separation. The first humans to reach Neptune may never see Earth again in 3 different senses. They may not see it with their eyes because it is too faint. They may not see it again physically because return may be impractical or impossible. And even if they return, they may never see the Earth they left, because decades of history will have transformed it into another world. A 30-year round trip is not simply long. It is a generational wound. A person leaving in 2026 would return in the late 2050s. The politics, technology, climate, culture, language, families, and cities of Earth would have changed. Children would become adults. Adults would grow old. Some relationships would survive as archives. Many would not. The crew would return famous, perhaps revered, perhaps traumatized, but not restored. The mission would not be a chapter in their life. It would be the central fact that consumed all other chapters. This is the exile horizon. Not a formal astronomical boundary, but a human one. It is the distance beyond which Earth stops functioning as operational support, emotional environment, visible object, rescue source, and shared present. It does not appear suddenly. It grows with distance. The moon lies inside it. Mars approaches it but remains, at least arguably, within human continuity. Jupiter strains it. Saturn bends it dangerously. Uranus pushes close to the edge. Neptune crosses it. The phrase is not meant to be precise. It is meant to name something that ordinary mission language hides. We speak of destinations as if all distance were quantitative. 3 days to the moon, months to Mars, years to Jupiter, decades to Neptune. But human experience does not scale linearly. A delay of 1 second is conversation. A delay of 20 minutes is correspondence under stress. A delay of 4 hours is a different social reality. A trip of 3 days is danger. A trip of 8 months is sacrifice. A trip of 15 years is a life. The science waiting at Neptune is extraordinary enough to tempt the argument back toward courage. A Neptune orbiter could transform planetary science. It could measure the planet's gravitational field, magnetic geometry, atmospheric composition, internal heat flow, and ring dynamics. It could study why Neptune's winds are so fast, why its storms form and vanish, how its tilted magnetic field is generated, and how ice giant interiors behave under pressures that turn familiar molecules into unfamiliar phases of matter. It could resolve questions about the common class of exoplanets, often described as Neptune-sized or sub-Neptune worlds, which appear abundant around other stars. Triton alone could justify a mission. It is one of the strangest moons in the solar system. Large, retrograde, likely captured, geologically young, and active despite extreme cold. Its surface temperature is around -391 degrees Fahrenheit. Voyager saw dark, geyser-like plumes rising from its nitrogen ice surface. Triton may contain a subsurface ocean, although this remains uncertain. If it does, then a captured Kuiper Belt object orbiting the 8th planet could belong to the family of ocean worlds, where chemistry, energy, and liquid water might intersect in ways relevant to astrobiology. Imagine the first close human-led exploration of Triton. Not necessarily a landing by astronauts on the surface, which would be far more dangerous, but a crew in orbit directing robots with almost no delay, making decisions in minutes that would take Earth-based teams 8 hours of round-trip communication. They could fly drones or hoppers through plume fallout if such technology existed. They could choose targets based on fresh data. They could repair instruments, adapt mission plans, and respond to discoveries in real time. The science return could be unlike anything a fully Earth-controlled robotic mission could achieve. This is the strongest pro-human argument. Humans near Neptune would be scientifically powerful because they would restore local immediacy. They could not speak to Earth in real time, but they could speak to their machines in real time. They could think beside the data instead of waiting for it to crawl across the solar system. The farther a destination is from Earth, the more valuable local intelligence becomes. A crew at Neptune could make the Neptune system responsive to human curiosity in a way no distant control room can. The objection is formidable. Robotic autonomy is improving. Artificial intelligence may allow future probes to make many decisions without waiting for Earth. A well-designed robotic mission could orbit Neptune for years, fly by Triton dozens of times, deploy an atmospheric probe, study rings and moons, and return science without risking human lives or building a habitat that must sustain people for decades. The cost difference would be enormous. The ethical difference would be enormous. If the scientific question can be answered by robots, sending humans may be an act of symbolism rather than necessity. This is where the scientific argument must remain completely honest. A crewed Neptune mission is not scientifically required in the way a telescope or robotic orbiter is required. It would be an act of civilization-scale ambition. It would say that humans want not only to receive data from the outer darkness, but to place consciousness there, to have someone look at Neptune with eyes and know what it feels like to be a human being at the last major planet. That may matter, but it is not the same as a rational cost-benefit argument. There is another ethical layer. If a Neptune mission is one way, or likely one way, what does consent mean? Adult volunteers can choose danger. They can choose sacrifice. They can choose never to return. Human history is full of such choices, But institutions can also exploit the language of destiny to normalize abandonment. A mission that cannot rescue its crew must be honest from the beginning. It must not hide exile inside the word exploration. It must not imply return if return is a theoretical possibility with no practical architecture. It must not ask the public to celebrate courage while refusing to confront the moral cost of sending people where help cannot follow. A truly honest Neptune mission would need a different contract between civilization and crew. It would have to acknowledge that the crew are not merely employees on assignment. They are people crossing a boundary beyond the ordinary protections of society. They would need lifetime support before launch, psychological preparation unlike anything in current astronaut training, families integrated into the reality of delayed contact, and a mission architecture that treats autonomy as the core condition rather than a contingency. They would need authority to make decisions that Earth cannot supervise. They would need the right to prioritize survival over symbolic objectives. And if return is not realistically planned, that must be stated plainly. A civilization mature enough to send humans to Neptune may also be mature enough not to send them. That may be the most controversial version of the argument. The public imagination often treats human presence as the highest form of exploration. Robots are scouts. Humans are the real story. But Neptune challenges that hierarchy. It asks whether the desire to put human eyes at the edge of the planetary system is worth exposing living people to an isolation so complete that it changes the meaning of personhood. It asks whether the heroic narrative of spaceflight, shaped by flags, footprints, and returns, can survive a mission whose most honest symbol is not a flag planted on a surface, but a delayed message from a crew who may never come home. The pro-human reply is not weak. Exploration has always changed the explorers. The fact that a journey is irreversible does not automatically make it unethical. Some of humanity's greatest transformations have come from migrations with no return. A future crew might see Neptune as a place not of loss, but of beginning. They might establish a permanent research habitat in orbit, supported by nuclear power and periodic robotic cargo sent decades in advance. They might become the first residents of the outer solar system, pioneers of a new human branch rather than victims of exile. But permanent presence at Neptune only deepens the question. A colony there would not be like a base in Antarctica. It would be dependent on machinery, nuclear power, imported resources, and closed ecosystems in an environment where solar energy is weak and local materials are difficult to use. Triton may offer nitrogen, water ice, and other volatiles, but exploiting them at scale would require an industrial base that does not exist. Neptune itself has no solid surface. Its gravity well is deep. Its atmosphere is violent. Its rings are tenuous. The system is scientifically rich, but not obviously hospitable to industry. Perhaps future technology changes this. Fusion power, advanced robotics, in situ resource utilization, radiation shielding from local ice, artificial gravity habitats, molecular manufacturing. The honest argument leaves the door open, but it does not confuse openness with inevitability. The mere fact that a future technology can be named does not mean a mission plan can depend on it. For now, the only realistic path to Neptune is robotic. A flagship-class orbiter and probe could do science that Voyager 2 could not. It could spend years where Voyager spent hours. It could study Triton as a possible ocean world. It could reveal the structure of Neptune's atmosphere and magnetic field. But even robotic Neptune missions are hard enough that planetary science priorities have favored Uranus in the near term, partly because reaching and operating at either ice giant is demanding, and Uranus offers a more accessible target for a new flagship. Neptune is not neglected because it is boring. It is delayed because the solar system is large. That is the central revelation. The outer solar system is not a place waiting patiently for human arrival. It is a scale problem so severe that it reorganizes ethics, engineering, psychology, and language. Neptune is local in astronomical terms, but extreme in human terms. The nearest stars are thousands of times farther, but Neptune already breaks the assumptions of human exploration. Before interstellar travel becomes the serious challenge, the eighth planet quietly demonstrates that even our own system contains distances that human culture is not yet built to absorb. Think again of the first crew arriving. After years of transit, the blue point ahead has swollen into a world. Neptune fills the window, not as a poster color but as a living atmosphere. Dark bands curve across it. High methane clouds catch the faint sunlight. Storms move with speeds no sea on Earth has ever known. The rings appear as fine, dusty arcs. Triton moves in retrograde silence, a captured world circling the wrong way, its surface young and cold and scarred by geysers that once surprised the only spacecraft to pass. The crew has reached something magnificent. They have also reached a place where no one can reach them. Their first transmission after orbital insertion might be carefully rehearsed, a statement for history, a human voice from Neptune. It leaves the spacecraft and travels inward, past Uranus, past Saturn's orbit, past Jupiter's enormous domain, across the asteroid belt, past Mars, toward Earth. For hours, no one hears it. On the spacecraft, the crew has already moved on to system checks, trajectory confirmation, power management, health monitoring. The moment that will become historic on Earth has already become work for them. Then, at last, the signal arrives. People on Earth listen. They celebrate. They cry. They replay the words. They send a response. Congratulations. We heard you. Humanity is with you. The response races outward at light speed. It reaches the crew hours later. By then, the insertion burn is old news. A coolant loop has drifted above nominal. Someone is exhausted. Someone is trying not to think about the return trajectory. The celebration arrives as an echo from a world that cannot share the moment when it happened. This is the loneliness that technology cannot entirely remove. It is possible to build better radios. It is possible to compress data, increase transmitter power, use laser communications, deploy relay networks, and automate mission operations. None of that changes the speed of light. A perfect communication system at Neptune still delivers an 8-hour round trip. A perfect rescue architecture still cannot violate travel time. A perfect telescope still shows Earth as an object, not a presence. The core barrier is not signal quality. It is simultaneity. Earth and Neptune cannot share human moments the way Earth and orbit can. The language of space exploration has not yet adapted to this. We still speak as though destinations are simply more distant places. But the outer solar system demands a vocabulary of separation. A mission to Neptune would not just travel through space, it would travel out of the shared human present. The crew would remain biologically human, culturally human, intellectually human. But their relationship to humanity would be mediated by delay, distance, and irreversibility. They would be representatives of Earth who can no longer be held by Earth in real time. Maybe that is why Neptune is so powerful as a subject. It is not the most massive planet. It is not the most visually famous. It does not have Saturn's rings or Jupiter's great red spot. It has not received the obsessive attention Mars receives. But Neptune makes the solar system morally large. It shows that the boundary of human belonging is not identical to the boundary of the sun's gravity. A world can be ours and still be almost unreachable. A destination can be inside the family and still require leaving the family behind. There is a humility in that. The solar system is not a human-scaled environment. It never was. We made it human-scaled with diagrams, names, myths, and missions that reached only the nearest shores. The moon allowed us to believe space could be crossed and returned from. Mars invites us to believe the frontier can be extended. Neptune whispers a colder lesson. Distance is not only a challenge to overcome, it is a condition that changes the meaning of overcoming. If humans ever reach Neptune, they will deserve admiration. Not because they conquered the outer solar system, but because they accepted what could not be conquered. They would accept delayed speech. They would accept no rescue. They would accept a sun reduced to a point and an earth reduced to memory. They would accept that their greatest discoveries might be celebrated by people they cannot hear in the moment, on a planet they cannot see, under daylight they may never feel again. That does not make the mission meaningless. It may make it too meaningful to treat casually. The mistake would be to turn Neptune into a simple warning. Do not go. It is too far. That is too small a conclusion. The better conclusion is that Neptune forces the human species to distinguish between exploration, occupation, exile, and sacrifice. Robots can explore without suffering. Humans can explore, but they bring bodies, minds, relationships, and moral obligations. A civilization that ignores those obligations in the name of destiny is not brave. It is careless. A civilization that faces them clearly may one day decide, with full honesty, whether the journey is worth the cost. For now, Neptune waits. It turns slowly in the dim light, whipping its clouds around itself with impossible winds. Its largest moon circles backward, a captured ghost from the Kuiper Belt. Its rings hold fragile arcs of dust. Its atmosphere radiates internal heat into darkness. Its blue face receives sunlight that left the sun 4 hours earlier, a pale remnant of the star that floods Earth with day. And somewhere, in the inner solar system, we look at diagrams and call it the 8th planet, as if a number could make it close. Neptune is not the edge of the solar system. The Kuiper Belt continues beyond it. The scattered disk reaches farther. The Oort cloud, if imagined as the sun's distant cometary shell, extends almost into interstellar space. The heliopause, where the solar wind gives way to the interstellar medium, lies beyond Neptune. The sun's gravity reaches farther still. By astronomy's measures, Neptune is not the end, but for human beings, it may be the first true end of something. It is the end of real-time help, the end of visible Earth, the end of rescue as an operational assumption, the end of sunlight as a familiar presence, the end of exploration as a temporary departure from home. It is the place where the solar system stops feeling like a neighborhood and reveals itself as an ocean so wide that even the nearest shore can vanish. The first humans to reach Neptune would not stop being human. That is exactly why the journey is so unsettling. Machines can travel far without caring. People carry home inside them, and home is not infinitely stretchable. It is made of light, voice, touch, timing, rescue, memory, shared grief, shared joy, and the knowledge that if you call out in fear, someone can answer while fear is still happening. At Neptune, the answer arrives hours later. That is why the planet matters. Not only because it is beautiful, not only because it is scientifically rich, not only because Triton may hide an ocean, or because Neptune's winds challenge our models, or because ice giants are keys to understanding worlds around other stars. Neptune matters because it asks whether human expansion has a psychological boundary inside the solar system itself. Maybe one day we will cross it. Maybe the crossing will be a triumph. Maybe the first crew at Neptune will speak with calm voices, run their experiments, orbit Triton, and look back toward the unseen Earth with pride rather than sorrow. Maybe they will not call themselves exiles. Maybe they will call themselves the first outer system humans, but the physics beneath the poetry remains. Their words will take hours to reach us. Our gratitude will take hours to return. If they are in danger, we will know too late to stand beside them. If they look for Earth, they will need an instrument. If they come home, the world they return to will not be the world they left. And if they do not come home, Neptune will become the first place inside our own solar system where human presence became permanent, not by settlement, but by separation. This is the argument hidden behind the blue planet. The unsettling part of Neptune is not that it is beyond reach. It is that it is barely within reach, and that may be worse. A truly impossible destination asks nothing of us. A reachable exile asks everything. It asks for technology, courage, honesty, and a willingness to admit that not every place we can imagine visiting should be described with the comforting language of ordinary exploration. There are distances that turn a journey into a life. There are delays that turn conversation into archaeology. There are missions that do not extend home, but reveal where home ends. Neptune, cold and blue and violently alive under a twilight sun, is one of them. It orbits our star. It belongs to our system. It appears on our posters. It has been known since a mathematician predicted where an unseen world must be, and a telescope found it within the sky. It is not alien in the interstellar sense. It is part of the architecture that made Earth possible, part of the gravitational story of the planets, part of the same cosmic neighborhood. And still, for the first humans who reach it, Earth may become invisible, unreachable, and finally unrecoverable. To see how much the classroom picture has hidden, look at how Neptune entered human knowledge in the first place. Mercury, Venus, Mars, Jupiter, and Saturn were known to ancient sky watchers because they move brightly enough against the fixed stars to be seen by unaided eyes. Uranus was discovered with a telescope, and even then it was first mistaken for a comet. Neptune went further. It was found through a disturbance. Uranus did not move exactly as expected. Its orbit showed small deviations from the path predicted by Newtonian gravity after accounting for the known planets. Those deviations could have been many things: observational error, incomplete mathematics, a hidden mass, or a misunderstanding of gravity itself. The successful answer was a hidden planet. Urbain Le Verrier calculated where that unseen body should be. Johann Galle pointed a telescope at the predicted region in 1846 and found Neptune close to the expected position. The eighth planet entered history not as a bright wanderer, but as a correction term in the motion of another world. That origin matters symbolically because Neptune has always resisted direct human intuition. It was not discovered by sight first, but by the pressure it placed on equations. It remains that kind of planet. You do not feel it, you do not see it, you infer it, calculate it, amplify its faint light with instruments, and wait hours for a signal from any machine near it. Neptune is a planet of delayed knowledge. The same is true of its moon Triton. Triton was found soon after Neptune, but its meaning became clear much later. Its retrograde orbit is a fossil of violence. A large moon moving backward around a planet almost certainly did not form from a calm disk of material around that planet the way many regular moons did. It was likely captured. The capture of a world as large as Triton would have shattered or scattered whatever satellite system Neptune had before. The Neptune system we see today may be the aftermath of an ancient gravitational crime, a Kuiper belt object seized by an ice giant, its companions destroyed or expelled, its orbit slowly reshaped by tides. A human crew at Neptune would not simply arrive at a distant planet. They would arrive inside a crime scene from the early outer solar system. Triton's surface is young by crater-counting standards. Its nitrogen geysers are not just scenic curiosities. They are clues that energy still moves through a moon where sunlight is almost irrelevant. Perhaps seasonal solar heating of dark surface deposits drives some plume activity. Perhaps internal heat contributes. Perhaps a buried ocean persists, protected by ice and chemistry. Each possibility changes what Triton means. If it is an ocean world, then liquid water may survive even at the edge of planetary daylight. If it is mainly a seasonal geyser world, then weak sunlight can still trigger geologic activity through clever surface physics. If it preserves Kuiper belt chemistry, then Neptune's captured moon may contain records of planet formation that no inner world mission can provide. This is why a robotic Neptune orbiter would be one of the most scientifically powerful missions ever flown. It could answer questions that Voyager 2 only opened. It could measure gravity fields, map magnetospheres, watch storms through seasons, sample the atmosphere, and fly repeatedly past Triton. It could reveal whether the ice giant interior models we apply to exoplanets are trustworthy. It could show whether Neptune's ring arcs are maintained by resonances, collisions, or more fragile processes. It could measure isotopes in the atmosphere and reconstruct where Neptune formed before it migrated outward. All of this matters because Neptune-like planets are common around other stars. Understanding Neptune is not local trivia. It is a calibration problem for planetary science across the galaxy. And yet the very strength of the robotic case weakens the case for sending humans. A robot can wait. A robot can survive on little power. A robot can accept a mission profile whose human equivalent would be ethically impossible. A robot can arrive after 16 years and still be, in the only sense that matters, fresh. Its instruments may age, but it does not miss children growing up. It does not fear that its spouse has become a stranger. It does not need to process the emotional weight of knowing that no rescue can come. When people say humans should go because humans are more adaptable than robots, they are partly right. But adaptability is not free. It is paid for by minds and bodies that can suffer. The pro-human case, therefore, has to be narrower and more honest. Humans at Neptune would be valuable if the science required flexible judgment under local time, physical repair, complex fieldwork, or real-time control of robotic systems around Triton. Humans would be valuable if the mission goal were not only data, but the expansion of human experience into a realm no one has directly witnessed. Humans would be valuable if the civilization sending them accepted the cost without hiding it behind slogans. But humans would not be valuable simply because a footprint is more emotionally satisfying than a dataset. On Neptune, there is no surface to stand on, and on Triton, a footprint would be a far smaller achievement than surviving the system that carried the boot there. The rescue problem also has a hidden engineering layer. It is not enough to say that no rescue can arrive quickly. A rescue mission would need to know what failed, match the trajectory, carry compatible parts, intercept a spacecraft moving through the outer solar system, and do so with a launch window dictated by planetary positions rather than urgency. Earth cannot simply point a rocket at a distressed crew and accelerate until help arrives. Deep space navigation is not a straight emergency road. It is a choreography of energy, timing, gravity, and propellant. A rescue vehicle fast enough to matter would require propulsion far beyond the technology assumed for the original mission. If such propulsion existed, it would have been used by the original mission already. Even cargo support is not simple. One might propose sending resupply packages ahead of the crew, staging materials along the route or at Neptune orbit. This could reduce risk. It is a serious idea. But every depot must arrive, survive, maintain temperature, preserve parts, avoid orbital hazards, communicate, and remain accessible after years or decades. Each depot becomes another mission. Each mission has launch costs, failure modes, and trajectory constraints. A Neptune expedition supported by pre-positioned infrastructure starts looking less like one mission and more like a program lasting generations, with dozens of launches, nuclear power sources, autonomous navigation, and a level of political continuity that modern space programs rarely sustain. Political continuity matters because Neptune punishes short attention spans. A Mars program can be imagined within a political career, even if it stretches beyond one administration. A Neptune human program would likely span the adulthood of the engineers who begin it, and the childhood of the people who finish it. The launch vehicle, habitat, power system, propulsion system, medical architecture, food systems, ground infrastructure, communication networks, and robotic precursors would have to survive changes in government, funding, public enthusiasm, economic crisis, and technological fashion. The mission's greatest vulnerability might not be a meteorite. It might be a budget cycle. This is another place where science fiction deceives us. Fiction begins when the ship launches. Real missions begin decades earlier with requirements, documents, test facilities, political arguments, procurement failures, redesigns, material shortages, risk reviews, public opposition, and the slow attrition of institutional memory. A crewed Neptune mission would require not only a spacecraft that can survive decades, but an Earth civilization that can remain committed long enough to build, launch, support, and receive it. If the crew takes 15 years to arrive and 15 years to return, the ground organization supporting them must persist for longer than many national space priorities have ever remained stable. Even if the mission is one way, Earth still has obligations. A one-way crew at Neptune is not an abandoned crew. It would require communication support, scientific processing, psychological support, political legitimacy, and probably periodic robotic cargo for as long as the habitat exists. If the sending civilization loses interest after the dramatic arrival, the mission becomes a monument to the danger of turning exploration into spectacle. The crew's isolation would deepen not because light speed changed, but because society looked away. This is why the word exile must be handled carefully. Exile can be forced, and that would be monstrous, but exile can also be chosen, embraced, and transformed into identity. The first generation of humans who went to Neptune permanently might not experience themselves as victims. They might see themselves as founders of an outer system culture. They might create rituals around the 4-hour delay, around the dim sun, around the first sight of Triton, around the fact that Earth is a coordinate rather than a visible home. Human cultures are astonishingly good at making meaning from limits, but a culture cannot be assumed before it exists. A mission planner cannot say, the crew will simply adapt, and treat that as an answer. Adaptation is a hypothesis that must be tested, supported, and made survivable. The difference between a chosen frontier and a slow psychological collapse may depend on habitat volume, social structure, privacy, authority, conflict resolution, access to meaningful work, reproductive policy, communication norms, and the crew's ability to shape their environment rather than merely endure it. The ethics becomes even sharper if the mission lasts long enough for children to be born during transit or in a Neptune habitat. A first crewed mission is not a multi-generational settlement, yet any permanent or very long human presence raises the same question and carries the same ethical burden. Adults can consent to exile. Children cannot consent to being born beyond the rescue horizon. A society at Neptune would have to decide whether to reproduce, knowing that any child born there inherits a world with no natural biosphere, no open sky, no Earth within sight, and perhaps no practical return. That is not a simple argument against such a society. Human children are always born into conditions they did not choose. But the degree of environmental dependence at Neptune makes the moral burden much heavier. There is also a philosophical danger in treating distance as destiny. People sometimes romanticize harsh frontiers because harshness gives stories weight. The outer solar system can become a stage for fantasies of purity, toughness, and escape from Earth. But a Neptune mission would not free humans from dependence. It would make dependence more precise. The crew would depend on the integrity of pressure seals, the stability of nuclear reactors, the sterility of water loops, the judgment of a handful of doctors and engineers, the behavior of closed ecosystems, and the reliability of machines whose failure modes may be unknown until they fail. The farther from Earth they travel, the less independent they become in the ordinary human sense. They do not become rugged individuals. They become organs inside a spacecraft. That image is uncomfortable, but useful. A human body survives because organs cooperate, because oxygen moves, because waste is removed, because temperature is regulated, because repair happens constantly at cellular scales. A Neptune spacecraft would be an artificial body. The crew would live inside it and maintain it, but they would also be maintained by it. If one system fails, all lives are affected. There is no outside environment to buffer the failure. There is no river to drink from, no forest to forage, no atmosphere to breathe, no soil to plant unless the soil or its substitute was carried or built. Independence from Earth becomes total dependence on the vessel. The vessel, in turn, depends on a fact that is easy to forget. Every machine ages. Deep space is not empty in the engineering sense. It contains radiation. It contains micrometeoroids. It contains thermal cycling, vibration, outgassing, lubricant degradation, electronics aging, and the slow migration of atoms through materials. A pump that works perfectly in year 1 may not be the same pump in year 12. A valve that cycles 1,000,000 times may not seal the way it sealed in testing. A plastic component may become brittle. A cable insulation layer may crack. A sensor may drift by a small amount that matters only after it has misled a controller for months. Redundancy helps, but redundancy is a resource that is spent. If there are 3 carbon dioxide removal units and 1 fails, the system is still safe. If the second fails, the mission continues with fear. If the third begins to show anomalies, the crew lives at the edge of a cliff. Repair can restore redundancy only if the tools, parts, time, and knowledge remain available. Neptune turns every spare part into a moral object. A bearing is not a bearing. It is months of water security. A filter is not a filter. It is respiratory confidence. A circuit board is not a circuit board. It is the difference between knowing what the reactor is doing and guessing. This is why the crew must be more than specialists. On the International Space Station, astronauts are trained broadly, but they are backed by thousands of specialists on Earth. At Neptune, the crew must internalize enough of that expertise to act without immediate guidance. The physician may need to perform surgery. The engineer may need to improvise a biochemical fix for crop failure. The pilot may need to become a plumber. The botanist may need to diagnose psychological burnout. The commander may need to decide whether to abandon a mission objective to save a subsystem that Earth still believes is healthy because the telemetry they are seeing is hours old. Autonomy sounds heroic until it becomes loneliness with responsibility attached. The communication delay creates another subtle problem. Authority. Who commands a Neptune mission in a crisis? Earth has strategic authority because it represents the civilization that built the mission. But the crew has situational authority because only they know the current state. With an 8-hour round trip, ground control cannot command moment-by-moment operations. It can recommend, analyze, and support, but it cannot supervise. A serious Neptune architecture would need to grant the crew far more decision-making power than any crewed space mission has granted before. That power could create tension. Suppose Earth wants the crew to attempt a risky Triton flyby because the scientific return is enormous. The crew knows that a navigation subsystem is behaving slightly outside its envelope, but the data are ambiguous. Earth sees the same issue hours later and judges the risk acceptable. The crew feels the vibration, sees the crew fatigue, knows which spare parts are low, and decides the risk is not acceptable. Who decides? In low Earth orbit, mission rules and real-time discussion resolve such conflicts. At Neptune, the answer has to be built into the political and ethical structure before launch. A crew beyond the exile horizon cannot be managed like a remote instrument. They must be trusted as a local civilization in miniature. That phrase points towards the deepest transformation. A Neptune crew, especially on a one-way or multi-decade mission, is not simply a crew. It is a small society. It must govern itself, maintain justice, resolve conflict, care for illness, distribute labor, protect privacy, preserve purpose, and decide what to do when mission plans collide with lived reality. Space agencies are excellent at procedures. Societies require more than procedures. They require legitimacy. How does legitimacy function in a crew of 6 after 10 years? What if one member refuses a dangerous repair? What if 2 members form a relationship and the others believe it affects operational fairness? What if someone develops severe depression and cannot perform duties? What if the commander loses trust? What if a scientific objective requires exposure to risk that half the crew rejects? These questions are not distractions from the engineering. They are part of the engineering, because human behavior is a mission system. The strongest argument for never sending humans to Neptune with near-current technology is not that any one of these problems is unsolvable. It is that all of them must be solved at once, for decades, with no rescue, under delay, in a vehicle that cannot rely on the planetary support structure that makes advanced technology possible. The strongest argument for eventually sending humans is that solving them would mark a new phase of civilization, one in which human communities can function at the scale of the solar system rather than the scale of Earth. Both arguments are serious. That is why Neptune is not a simple no. It is a test of what kind of yes we are willing to defend. There is another objection, and it may be the most optimistic one. Perhaps the first humans to Neptune would not travel in a small spacecraft at all. Perhaps by the time such a mission is attempted, humanity will have built a deep infrastructure through the outer solar system. Nuclear-powered shipyards near the asteroid belt, propellant production around Jupiter's moons, autonomous cargo routes to Saturn, habitats in orbit around Uranus, and robotic factories that make long journeys less like heroic leaps and more like difficult logistics. In that future, Neptune would not be reached from Earth in one desperate throw. It would be reached from a chain of outposts, each one extending the practical boundary of rescue and supply. That future is possible in principle. It is also a different civilization from ours. It would mean humanity had already solved most of the problems that make Neptune so difficult. It would mean large-scale nuclear or fusion power in space, reliable autonomous manufacturing, mature closed-loop life support, artificial gravity habitats, radiation protection, and political continuity across centuries of solar system development. If those conditions exist, then Neptune is no longer the first great exile. It becomes the outer station of a society that has already learned how to live far from Earth. But this counter-argument quietly concedes the main point. It says Neptune becomes humanly approachable only after we move the meaning of home outward, not by a single mission, but by building new homes along the way. The exile horizon is not fixed in kilometers. It depends on infrastructure. A city on Mars would change the meaning of Mars. A thriving Jovian system would change the meaning of Saturn. A civilization distributed through the giant planets would make Uranus less lonely and Neptune less absolute. The horizon can move, but it does not disappear. It moves because belonging has been rebuilt, not because distance stopped mattering. For the first crew traveling directly from Earth, without that chain of established worlds, Neptune remains a psychological cliff. The difference between a frontier and an exile is not simply distance. It is whether a social world extends with you. A person who moves to a new continent is far from birthplace, but not outside society. There are cities, languages, laws, neighbors, markets, doctors, roads, graves, and children. A person alone in a lifeboat has no frontier, only survival. A Neptune crew without outer system infrastructure is closer to the lifeboat than to the continent, even if the spacecraft is technologically magnificent. This is why the first human Neptune mission, if it ever happens, should probably not be the first human outer system society. It should come after many robotic missions, after long-duration habitats closer to the sun, after artificial gravity has been tested for years, after nuclear space power has become routine, after autonomous medicine has proven itself, after crews have lived at Jupiter or Saturn distances long enough to teach us what isolation at that scale does to human beings. A mature path to Neptune is incremental. The dramatic path is a leap. Drama is not the same as wisdom, and yet there will always be voices arguing for the leap. They will say humanity advances by refusing to wait until every risk is solved. They will say no ship would ever have crossed an ocean if sailors demanded certainty. They will say the first people to Neptune will know the cost and choose it. They will say that some achievements require a willingness to become the bridge for people who come later. These arguments should not be dismissed with cynicism. They come from a genuine human impulse, the same impulse that made us leave valleys, cross ice bridges, build boats, climb mountains, and eventually send machines beyond the planets. The answer is not to mock ambition. The answer is to discipline it. Disciplined ambition says that a Neptune mission must not use false analogies. It must not borrow the romance of sailing ships while ignoring that sailing ships moved through air, water, food chains, and rescuable geography. It must not borrow the language of Apollo while ignoring that Apollo's delay was seconds and its duration days. It must not borrow the confidence of robotic success while ignoring that robots do not need society. It must state the cost in the correct units, not only dollars, kilograms, and years, but autonomy, aging, irreversibility, and the loss of shared time. The loss of shared time may sound abstract until you imagine ordinary life aboard the mission. A crew member records a message for a child on Earth. They speak carefully because the child will not answer in the moment. They ask about school, about a birthday, about a drawing taped to a bedroom wall. 4 hours later, the child receives it. Perhaps the child answers immediately. 4 hours after that, the reply reaches the spacecraft. The crew member smiles at a face from 8 hours of history. It is still love. It is still communication, but it is not presence. And over 15 years, the difference between communication and presence becomes a canyon. A mission can survive without presence. Soldiers, migrants, prisoners, researchers, sailors, and astronauts have survived long separations. The question is, what happens when separation is not a season, but a structure? When every relationship with Earth is permanently converted into delayed media, human attachment may adapt. It may also withdraw. The crew may begin to invest emotionally only in those physically aboard, because only those people can answer now. Earth becomes the archive of former attachments. The ship becomes the only living society. That shift may be necessary for survival. It may also be the moment when the crew stops psychologically belonging to Earth. There is no shame in that. It may even be beautiful in a severe way. A small human community circling Neptune, building meaning under a twilight sun, studying Triton, maintaining its systems, creating rituals around delayed messages, and accepting that Earth is origin rather than home would be one of the most profound transformations in human history. But it would not be a conventional mission. It would be the birth of a diaspora inside the solar system. The word diaspora is important because it holds both loss and continuity. A diaspora carries memory forward after separation. It creates new identity without wholly abandoning the old. If humans ever live at Neptune, they may become the first true solar diaspora, not because they crossed to another star, but because they crossed beyond the practical immediacy of Earth. Their culture would begin with a paradox. They are humans from Earth who cannot live as Earth humans anymore. That possibility gives the story its final tension. Neptune is unsettling because it can turn Earth into memory. Neptune is also compelling because memory is not nothing. Much of human civilization is built from memory. Ancestors, migrations, vanished homes, old languages, origin myths, founding journeys. A Neptune society could survive by turning Earth into such a mythic center. The danger is that myths can sustain people, but they can also harden, distort, and lose contact with the living world that created them. The first crew would stand at the point where those futures diverge. Behind them, Earth, delayed and invisible. Around them, machinery. Beneath them, an ice giant. Nearby, Triton, carrying the scars of capture and the possibility of an ocean. Ahead, either return, permanent habitation, or a slow expansion of human meaning into the outer dark. No classroom diagram contains that. There is a quieter way to phrase the conclusion. The first humans to reach Neptune would not necessarily be doomed, but they would be changed before arrival. Their mission would demand that they stop thinking of Earth as a place beneath them, like station astronauts do. Stop thinking of Earth as a nearby world in the sky, like Apollo astronauts did. And stop thinking of Earth as a delayed but practical support base, as Mars crews might. They would have to think of Earth as origin, a beginning, a voice in the archive, a source of memory and meaning, but not a participant in the present. Civilizations have origin stories. Individuals have homes. A Neptune crew would be forced to let the first become more important than the second. Perhaps that is the cost of becoming a solar system species. Perhaps every outward step requires that home become less immediate and more mythic. The Moon gave us Earth as a whole planet. Mars will give us Earth as a delayed partner. Neptune would give us Earth as a vanished light. Each step outward changes the image of home. The question is whether the human mind can follow that image without breaking, or whether there is a distance where the mind can understand the mission, but the heart cannot live inside it. The old diagrams cannot answer this. They only show positions. They cannot show what a 4-hour delay does to grief. They cannot show what 30 astronomical units do to rescue. They cannot show what twilight noon does to a brain built under blue sky. They cannot show what it means to celebrate a discovery and then wait half a day for humanity's joy to return. This is why Neptune deserves more careful language. It is not merely remote. It is not simply cold. It is not just the last planet. It is a mirror held up to the hidden assumptions of human expansion. We assume that if a place is inside the solar system, it is in some future sense reachable. We assume that reachability means continuity. We assume that continuity means return, communication, support, and shared triumph. Neptune breaks those assumptions without leaving the Sun's domain. It shows us that the solar system has an inner human zone and an outer human question. The inner zone is where Earth can still function as home base. The outer question is whether human beings can live meaningfully where Earth cannot function that way anymore. Neptune belongs to that question. It does not answer it. It asks it with a blue face and a dim noon and a silence 4 hours wide. And the answer for now is uncertain. The same reframing changes how we should think about mission success. A Neptune crew might reach the system, complete every planned observation, return beautiful data, and still reveal that the central assumption was wrong. Success would not prove that the distance was humanly easy. It would prove only that one carefully selected group, inside one carefully built machine, under one historical alignment of funding and technology, survived a path that remains unforgiving. We should resist the habit of turning survival into proof of safety. Spaceflight history is full of missions that succeeded while exposing risks no one had fully understood before launch. Likewise, a robotic mission failing on the way to Neptune would not prove Neptune is unreachable. It would prove that a specific architecture failed. The science of deep space exploration grows through these distinctions. Careful language matters because exaggerated certainty misleads both optimism and fear. Neptune is not a forbidden world. It is a world whose distance forces each claim to be stated with its conditions attached. A flyby is not an orbiter. An orbiter is not a crewed spacecraft. A crewed flyby is not a crewed orbital mission. A one-way habitat is not a round trip. A future with outer system infrastructure is not the same as a direct launch from Earth. This hierarchy of difficulty is where the debate should live. The public story collapses all of it into one dramatic sentence. Humans could go, or humans could not go. The scientific story is richer. Humans might someday pass Neptune. Humans might someday orbit it. Humans might someday live in its system. Each step demands not just more technology, but a different relationship with Earth. The farther the mission moves along that chain, the less it resembles exploration as return, and the more it resembles migration as transformation. There is also a subtle scientific humility in choosing robots first. A Neptune orbiter could tell us what hazards a human crew would actually face. It could map radiation environments, dust populations, ring hazards, magnetospheric variability, Triton's plume behavior, communications constraints, and navigation realities. It could identify potential orbital regions that are safer or more dangerous. It could test nuclear power systems, autonomy, and long-duration operations at the edge of the planetary system. Sending humans before doing that would be like sending a crew into an ocean we have barely sounded because the map looks inspiring. The outer solar system rewards patience. It took mathematics to find Neptune. It took Voyager 12 years to touch it with instruments. It may take a flagship orbiter decades from proposal to arrival. Human presence, if it ever comes, should be the result of accumulated understanding, not impatience disguised as destiny. The planet has waited 4.5 billion years. It will not be insulted if we learn how to survive the journey before asking people to live inside it. Until then, the most honest spacecraft we can send is the one that admits our limits while extending our senses. A machine can spend years crossing the dark without needing courage. It can arrive without nostalgia. It can look at Neptune, measure it, and teach us what the planet is before we decide whether anyone should one day pay the human cost of seeing it directly. That is not cowardice. It is the kind of restraint that makes future bravery less reckless. Even restraint can be a form of exploration when the unknown is large enough. It means looking at a blue world 4 light hours away and refusing to confuse desire with readiness. It means understanding that the first step toward Neptune may be humility, not speed, not fantasy. That uncertainty is the most honest place to end the argument. Not with a declaration that humans will never go. Not with a heroic promise that they certainly will. With the recognition that Neptune is close enough to tempt us and far enough to humble us. Close enough for robots, perhaps one day for people. Far enough that the people who go may not return, and even if they do, may return from an experience no previous human category can contain. That is why the first humans at Neptune would be more than explorers. They would be witnesses to the limits of the human world. Not because Earth is gone, because they are.